Okay, hi class. So second video might be a third video. These problems take a long time, but I wanted to follow up with finishing up 6.3. So last time, the last video, we finished up that problem, and I'll post the worked out part after the recurrence relation part. But so that was the one we were working on, and we finished the Frobenius part. Now I mentioned that there's a way we can kind of tell. Kind of check ahead of time how to know what R is, and that's called using the indicial equation. So the indicial equation helps us ahead of time know what R is, to know what R will be. So let me walk you through on how you do it. So the way you do it is there's kind of some steps involved, but it's kind of nice because it can be kind of, these problems take a long time and it's easy to make a mistake. So it's helpful to know what the indicial, what those R's will be ahead of time. So the way you do it is that you take your DE and you put it in the standard form. You do the Recurrence theorem. So you divide by the leading coefficient and you get it like that, okay? Then you form these kind of funky functions, which called little p. So little p of x is, you take this p of x function and you just multiply by x. That's how you do that. And same thing with little q. With little q, you just do x squared times q of x. Just a technical note. This is assuming that we're just going around the point of x equals 0. If it was a different term for like x for x naught, it would just be like p of x would be x minus x naught times big P of x, and q of x would be, x minus x naught quantity squared. So just FYI. But like I said, all the problems I assign will just be going around 0. Now we evaluate the functions at 0. Now it seems kind of weird that you're evaluating at 0, because won't that make that go away? Well, we'll see when we do a problem, but we're going to call that little p evaluated at 0. We're going to call that a naught. And I use this notation to kind of help us understand that we're evaluating at x equals 0. And little b naught will just be evaluating q at 0. Okay, so if you do all that, then you can plug it into this. This is called the indicial equation. And this, every single time, will tell you exactly what the R's are going to be ahead of time. So I think it's best to learn by doing. So let's look at the exact indicial equation from the last problem. So the last problem from example 1 was this: 3xy double prime plus y prime minus y is equal to 0. Okay, this is not in standard form. So, and by the way, we figured out ahead of last time when we did the problem that R1 was 0 and R2 is 2/3. So if we do the indicial equation, we should get the same thing, right? And we should get it ahead of time. Well, let's see. So if I do it, the first step is apparently I need to do Recurrence theorem. So if I do Recurrence theorem, divide everything by 3x, and then that gives me y double prime plus 1 over 3x y prime plus, now notice the Recurrence theorem has to be plus, so I need to include the negative in my q of x. So negative 1 over 3x y is equal to 0. So this helps me know that this right here is my big P of x, and this right here is my big Q of x, like that. Okay, so then I go to step 2. Step 2 says form little p of x. I think I had it in black here. Oops. So make this a little bigger. Okay, so then step 2 is form little p of x. So little p of x is equal to x times big P of x, which is going to be, if I multiply this by x, that cancels, and so it's just 1/3. Like that. Let's do the same thing for little q of x. So little q of x is defined as x squared times big Q of x, which, if I multiply this by x squared, just cancels, and you get negative 1/3 x, like that. Okay. All right. So according to the formula, so for 3, a naught is defined as p of 0 which is just going to be, it's just going to be this 1/3. This is always 1/3. Doesn't matter what 0 is. So that's what I meant by, multiplying by x times clear stuff out. So it's just 1/3. So that's done. And then b naught, what's that going to be? Well, that's q of 0, which is going to be this thing, negative 1/3 x, evaluated as 0. So times 0, and so just 0. Okay, so we found a naught, we found b naught, and then we just plug it into the formula. So the last thing is the formula says it's going to be r times r minus 1 plus a naught r plus b naught equals 0. Let's plug it in. So you get plug it in, and then you get 1/3 r plus 0 is equal to 0. And then you just solve it. So you r squared minus r plus 1/3 r is equal to 0. You get r squared minus 2/3 r. And then if you solve it, you get r times r minus 2/3. And so you get r1 is equal to 0, and r2 is equal to 2/3. And let's look back. Was that the exact same thing we found? Oh, yeah. So that's cool. So that's a quick way to do it before you do a problem, to be able to see what your R's are going to be ahead of time, which is great because these problems are long and it's easy to make a mistake. So it's helpful to know ahead of time what your indicials, your index R should be. Okay, so let's jump to a problem. So the last problem for this is that I want to work on solving this differential equation here. So I need more space. So let's go here. And I have a backup page with multiple pages in case. So is this problem here. Let's do the indicial equation first this time to kind of make sure that we're doing it okay, to kind of reinforce. So if we do it ahead of time, we also will know what R is, what the values of R will be, so we'll be ahead of the game. So let's try it. So I already did the step one. Step one was to do Rochelle's theorem. So I did that already. And then step two was to, kind of figure out what the x's and the p of x's, the little p and little q are. So this right here, let me do a different color. So this right here is going to be big P of x, and this right here is going to be big Q of x. Okay, all I did was I divided by the leading coefficient. I divided by 2x. All right, and so let's do the second step. So little p of x is going to be x times p of x, which in this case is just going to be 1 plus x over 2. Just make it simpler. 1 plus x over 2. Yeah. Okay, and then form little q of x. Little q of x is going to be actually x squared times q of x. That's from the formula. And that's going to be 1/2 x. That, just multiply that by x squared. Okay, so step three is you figure out what a naught and b naught are. So a naught is going to be p of 0, which is going to be 1. So this is p of x, so it's going to be just 1 plus 0 over 2, which is just 1/2. And then b naught is going to equal q of 0, which, just plug it in. So it's just going to be 1/2 times 0. So it's going to be 0. And so step 4 is that we just plug into the formula. I have it right here. So the formula is r times r minus 1 plus a naught r plus b naught is equal to 0. You plug that in, you get r times r minus 1 plus 1/2 r plus 0 is equal to that. You get r squared minus r plus 1/2 r equals 0. And you get r squared minus 1/2 r equals 0. Factor out an r, and you get r minus 1/2 equals 0. And so this tells me that r1 is going to equal 0, and r2 is going to equal 1/2, like that. Okay, so now we know ahead of time what r's are going to be. And if we do it wrong in the middle of the problem, this will help us know, like, oh, well, I did something wrong. So R1 and R2 are right there. So that's pretty cool. The indicial equation helps us do that. We'll keep that in the back burner for now. Let's go ahead and just jump to the problem. So again, you know, this is always going to be my guess for y, and so therefore this is what y prime is. Oh wow, I forgot the series. Whoopsies. Okay, n equals 0 to infinity. And then we're going to go ahead and just plug in. So next step is just you know, plug into the DE. So I'll just do 2x, and then we have y double prime plus 1 plus x y prime. Oh wow, I messed that up. That's the second derivative, folks. So I need to plug in the second derivative. So 2x y prime double prime n plus r minus 1 cn x to the n plus r minus 2. Okay, plus 1 plus x, this thing, n equals 0, n plus r cn x to the n plus r minus 1 plus y, which is just this. Okay, very good. By the way, I want to do something a little quicker this time. I'm going to factor out the x to the r at the very beginning. It's much, much faster, and I think maybe a little less confusing too. So you can factor out that x to the r here. I'm going to kind of cheat a little bit here, and I'm just going to say, you know what? Just factor out right here. Because they all share it. You know, they all have that x to the r in there. So now that's gone, and that's gone. And that's way more helpful. Now, the reason we care about that is that, you know, they're all, you know, just take out a like term. So I just factored it out, but then I can divide by it, you know, on both sides of that equation, and it doesn't matter. And, you know, if it were 0, it would be the trivial solution. So it's not 0. So that means that it's valid to do that, and we're all good. So now we have that. So that's step 1. I think that's faster. I should have done that in the last problem. Sorry about that. Next thing we can do is we can move this x into there. And so that's going to make that a minus 1, like that. And now the problem with this one is that we have these two terms. So we're going to get actually 2 series out of that. So let's start writing out what we have now. So, and I'm going to remember this time that we have 2 there. So we have 2, actually, why don't I just plunk it in? So we have the series 2n plus r, can't forget it now, minus 1, cn x to the n, no, the r's gone, and then I plugged in an x, so it's going to raise that up to minus 1, still starting at 0. I want to get 2 series out of here, so it's going to be this series. So if I just move in the 1 here, just, you know, get the series, n minus 1. Now, if I do this series where I have the x going in, that's going to raise that up. So it's going to be n plus r times cn times x to the n, x to the n, I guess, because that raised it up by 1. Okay. And then I have this one as well. Okay. And all that's equaling 0. So that's cool. Let me just double check. So 1, and then plug the x in, moves it up. Yeah, x to the n. All right. And I'll put that 2 in there, so I'll remember this time. Last time I forgot the 3. Okay. All right, so what are we going to do? Well, what can we do? So let's see. So these are already pretty much set. They have n equals 0, and they're starting at n. So I'm not sure what I want to do there. These are the problem children. So they started at n minus 1. So, and I want to move these up, but if I wanted to move these up, then I'd have to move that down, the index down, and I don't want a negative index. So I'm going to have to peel off the n equals 0 terms here. So I'm going to peel off for these two, for this series and this series. I'm going to peel off the n equals 0 term. And so you get n equals 0 for this first one would be 2 times r minus 1 c naught x to the negative 1. And for this one here, n equals 0, you get r c naught x to the negative 1, like that. Okay, so I have these peel off terms, and then I can, I know it's kind of tedious, but I'm going to write it all out just so we can kind of see. I didn't do that in the last video. So now if I have everything down, what do we have? Well, actually before I do that, then also for series 1 and 2, shift, you know what? I got time and I got space, so I'm not going to do too many steps at once. This will help you when you watch the video. If you're kind of can get where I'm going, you can kind of skip ahead a little bit. But so let's see what we have now. So now I have 2r minus 1 c naught x to the negative 1 plus r c naught x to the negative 1 plus the series now. All this junk starting at 1. 2n plus r n plus r minus 1 cn x to the n minus 1 plus series starting at 1, sorry, of n plus r cn x to the n minus 1 plus, you know, series number 3 and series number 4. But we haven't changed those, so don't worry about it. So I'll say plus 3 plus 4. Okay, so this is the peel off stuff right here. Now let's, so anyways, all this is still equaling 0. So the peel off stuff is important because it actually tells me what the r's are going to be. So let's work on the peel off stuff. So peel off terms. So I have this 2r times r minus 1 plus r, and they all share that c naught x to the negative 1. Well, that has to equal 0 because there is no x to the negative 1 terms here. So I can just set it equal to 0 because there's no x to the negative 1 term. That goes away and still equaling 0. And so what I really have is just this 2r times r minus 1 plus r has to equal 0. And then if we do it all out, we get 2r squared minus 2r plus r is equaling 0. And you get 2r squared, what is that, minus r is equaling 0. And you get r times 2r minus 1 equaling 0. And guess what, folks? Math is amazing because this is the same indicial equation that we had before when we did it earlier. And we figured out the same answers, that r1 is equal to 0 and r2 is equal to half, which is right here. So I'm going to put a big old smiley face right here, right here, right here, right here. So that's a big old smiley face. Makes me happy. Whoa, that was like a really bad smiley face. Okay. Well, anyways, celebrate all types of smiley faces. Okay. So that's cool. So those peel off terms is what gives us the indicial, those values of what R1 and R2 is. So that's cool. All right. So that's nice. Now let's work on the recurrence relation. So the recurrence relation will take from the series that we have now. You know, this is series 1, this is series 2. So let's work on series 1 and 2. Series 3 and 4 already start at 0 and have x to the n. These two don't have x to the n, but because they start at 1 now, I can go down 1 in index, so up 1 in formula. And if I do that, then we will get this. So we'll get n equals 0, 2 times, so again, go down 1 in the index, so up 1 in the formula. N plus r, now minus 1 plus 1 just cancels, and then Cn plus 1 x to the n, plus down 1 in the formula, up 1 in the formula, down 1 in the index, up 1 in the formula, Cn plus 1 x to the n. And then I still have, you know, that coming down and that coming down. No changes there. So n equals 0, n plus r, Cn x to the n, and Cn x to the n. Okay. All right, so all this is equaling 0, sorry. I had the peel-off terms, but the peel-off terms don't help me with the recurrence relation. Though that really just helped me with the indexes. So I can just work on this now with these 4 series, you know. And we just want to combine them to do the recurrence relation. So what would we do there? Well, let's see. They all share next to the n. So, and actually they're all like terms now, so we can just combine them all. And we get 2n plus r plus 1, n plus r, puts in a big bracket. This had a Cn plus 1 attached. This had this thing. This had this thing. And this just has Cn. Right? And all that has x to the n and equaling 0. So this is the big mushkila, which is means problem in Arabic. This is the thing that we want to care about. It's the recurrence relation that we'll work on. And that's cool. So let's go ahead and work on that. So recurrence relation time. I'm going to do some algebra because I noticed that they share a lot of stuff. For instance, they both have the Cn plus 1 right here. So if I factor that out, I'd have 2 times n plus r plus 1 times n plus r plus n plus r plus 1, all that times Cn plus 1. And then these guys share the Cn, so I have plus n plus r plus 1 times Cn, all that equals 0. All I did for this last one is kind of hard to see, but I just factored out the Cn. So if you went back and undid what I did right there, you would see that, yeah, they just go in and you get the same thing right there. Okay. So yeah, what else can we do? I noticed that this shares as well, which is going to actually help us, I promise. They share n plus r plus 1. So one last little bit of algebra I can do is I could factor that out as well. So I can factor it out here, and I'd have n plus r plus 1 times Cn plus 1. And what would be left inside? Well, I'd have a 2 in that, so I'd have 2 times n plus r, and then I'd have just a plus 1, like that. And you can watch this slower if the algebra is kind of tripping you up here on the YouTube video, but Cn is equal to 0. Okay, and in fact, I can get rid of this parentheses because it's just n plus r plus 1. All right, so let's go ahead and solve for this thing right there. Okay, so that means I'm going to subtract this thing from both sides. And what will we get? So we get 2n plus r plus 1 times n plus r plus 1, Cn plus 1 equals negative Cn over n plus r plus 1. like that. Now you can see why hopefully the algebra I did helped, because not divided. Oh, it's crazy. Crazy town. This is just times. So n plus r plus 1. Hopefully you can see why I did all that work, because you can kind of see that this is just going to cancel out with that, which is great. And then I could divide by this as well. And so you get Cn plus 1 is equal to negative Cn all over 2 times n plus r plus 1, like that. Which is really cool. Which I don't know if it matters to distribute or not. Probably not, but we can just kind of leave it like that. Yeah, I'll distribute and go one more step. So Cn plus 1 is equal to negative Cn over 2n plus 2r plus 1. Let's do that. Okay, well, that's cool. Again, then all that we do at the next step is, and this is true for our index, which was starting at 0. So over here. So it's true for n equals 0, 1, 2, 3, ... like that. All right, so then what do we do? Well, then you just plug in, your roots, your R1 and R2. And so you'd get, let's do R equals 0 first. So for R equals 0, you would get Cn plus 1 is equal to negative Cn over 2n plus 1. And that's for n equals 0, 1, 2, ... like that. Like that. So that's cool. And then for R1, so that's R1 equals 0. For R2 equaling 1/2, what do we get? We would get Cn plus 1 is equal to negative Cn over 2n. So if I multiply 2 by 1/2, I get 1. So plus 1 plus 1, which means Cn plus 1 is equal to negative Cn over 2n plus 2, which I'll just factor out as n plus 1. N equals 0, 1, 2, ... Like that. Okay. All right. So yeah, so that's what we get. And then you just do the recurrence relation thing. You just jump on it and do those things. I'm actually going to do it right now. So the video is going to be kind of long, but I'll do the entire one and check it out. So I have extra room over here. So let's do for R1 equals 0. So that one was Cn was Cn plus 1 was equal to negative Cn over 2n plus 1. And we'll work on it kind of separately here. For the other one, R2 was equal to 1/2. And this is for, n equals 0, 1, 2, ... This one was Cn plus 1 was equal to negative Cn over 2 times n plus 1, if I remember right. Yeah, for n equals 0, 1, 2, ... Okay, so let's just jump on it here. So for n equals 0, we get C1 is equal to negative C0 over 1. Okay, for n equals 1, I'm going to go kind of fast here. So n equals 1, C2 is equal to negative C1 over 2 times 1 plus 1, so 3. But I know C1 was up here, so it's going to be negative times negative, so positive C0 over 3. Okay, then we'll just keep on going. N equals 2. So it looks like C, it's all going to be terms in back of C naught. Let's make sure. So C3 is going to be negative C2 over 2. So 2 times 2, 4, 5, which is that. So it's going to be negative C naught over 5 times 3. That. Yeah, so it looks like they're all in terms of C naught. C4, boom, explosive, which is going to be negative C3 over 2 times 4, which is 8, 9. But that's going to be negative, negative, positive, C naught over 5 times 3. Oops, say 9 times 5 times 3. Like that. Okay. Did I do that wrong? Is it 7? It's 7. Yeah. Whoopsies. Okay, like that. So you can kind of see the pattern. It's alternating negative, positive, negative, positive. It's always in terms of C naught. So it looks like C naught is C naught. You know, we didn't have any information about it. So, so that's good to know. And then what else can we know? I think that's it. So if I wanted to write out this term here, let's see. So my guess for what y was that y was going to equal, you know, n equals 0, cn x to the n plus r. But guess what? We know that for this one, we know that here that r is 0. So that's just 0. So really our guess here is just, go back to here, is just y is equal to this, a regular old power series that we learned last time. So let's write out what that looks like. So y is equal to that, n equals 0, x to the n. Again, because for this r is 0, so that just went away. And so it's just going to be this, which is going to be c naught plus c1 x plus c2 x squared. You know, it's what every power series looks like. We don't know c naught, so c naught is just c naught. But we figured out that c1 was right here. So it's going to be, I'll just put a negative here, negative c1, negative c naught x. I'm going right here. So c1 is just equal to negative c naught. So negative c naught x. C2 we figured out was positive c naught over 3 x squared. We figure out C3 was negative C naught over 5 times 3. Try not to get negative while I'm forgetting my negatives. And so it's x cubed. The next one, C4, was plus C naught over 7 times 5 times 3, x to the 4th. Yada. Okay, so I know they all share the C naught, so I can pull that out, and then I'm just left with this. There is a way to write that using some fancy series and product notation. I don't really care. As long as we can kind of see that this is the pattern. And there we go, like that. Okay, so that's my y. Let's call that y1, because that's probably going to be linearly independent from what we find out. Oops, I say plus dot dot dot. Plus dot 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 dot. It's probably going to be separate from what we get over here. So let's see. So here for the R2 is equal to half. Let's just play the same game. So it starts at 0. So n equals 0. We get C1 is equal to negative C naught over just 2, like that. So I bet you that C naught is just going to be C naught. It's just going to be left over there. N equals 1. Oh, and by the way, just a notation. I should probably use different letters here, like call this K or something like that, or I don't know, or not that, but this C naught doesn't mean I'm saying this C naught. It's like 2 different problems now. I have 2 different indicial roots, so it's like 2 different power series now, just FYI. So n equals 1, what do we get? So we get n equals 1, C2 is equal to negative C1. 1, 2 times 2 is 4, like that. Okay, but we knew C1 was over here, so it's going to be positive C0 over 4 times 2. And then we keep on going. C3 is going to equal negative C2 over 2 times 2 plus 1 is 3, so 2 times 3, which is 6. Not, anyways, I'm pretty sure that's right. 2 plus 1, yeah, 3. 2 times 3. Okay. What was C2? It was C0, so it's going to be negative C0 over 4 times 3 times 2 times 2. I bet you there's going to be a pattern here. So C4, which is explosive, boom, is going to be negative C3 over 2 times 3 plus 1, which is 4. Which C3 was negative, so negative times negative is positive. So it's going to be positive C0 over 4 times 4 times 3 times 2 times 2 times 2. Wow, it's getting really, really big in the denominator. But we see a pattern. It alternates, positive, negative, positive, negative, positive, like that. I bet you I can play around with this a little bit. This looks like it's C0 over, I have, do I really care? Maybe. How many 4s do I have? I have 1, 2, 3. How many 2s do I have? I have 1, 2, 3 2s. This is like 2 squared. Yeah. I don't know. Oh, I have 4 times 3 times 2, so that's 4 factorial. So that's cool. 4 times 3 times 2, and then I have, 1, 2, this is, there you go. So it's like that. 2 to the 4. I wonder if that pattern holds here too. So this is going to be negative C0. Do I have 3 times 2? Yeah, so I have 3 factorial. And then I want 3 2s. So this is the factorial part. Then I have 1, 2, and I have, 2 2s. So 2 plus 1 is 3. Well, that's cool. That's neato. So this is going to be C0. This is like 2 factorial. And then do I have 2 2s? Yes, I do. 2 to the n, like that. And same deal. This is like negative C0. This is like 1 factorial. And it's like 2 to the 1. That. Well, that's cool. So this one did have a nice formula. If you're not super keen on that, it's not super important, but it is cool when it does happen. But anyways, let's write out what it is. So I think the formula is going to be Cn is equal to negative 1 to the n. It alternates. I have C0 every time. And then I have, looks like I have for, factorial. So n factorial to the n. Let's see though, you can always go back to here. So my guess again was this, n equals 0 to infinity, Cn x to the n plus r. Now I know what r is here. R is half, so just plus half, like that. So what's cool about that is that you can just pull it out. So you can just say, okay, I'm just going to pull out x to the half right here, and then just have this regular old power series that we're used to. And so that's going to equal x to the half times, what a power series is that we're used to. The power series is C0 plus C1x plus C2x squared plus C3x cubed plus dot, dot, dot. And so we get y is equal to x to the half on the outside, and then we get C0. C0 was C0. We didn't know what it was, but we did figure out what C1 was. C1 was minus, so right here, the C1 minus C0 over, 1 factorial over 2 times 2. The next one was right here, C2. So plus C0 over 2 factorial 2 to the n minus C0, just going down the line here, 3 factorial 2 cubed plus C naught over 4 factorial to the 4. Actually, it would be minus, but whatever. So we can kind of see the pattern here. So it looks like I can pull a C naught out, and so we get y is equal to C naught x to the half times all this stuff. 1 minus 1 factorial over 2 plus 1 over 2 factorial to the, this was 2 squared. 2 squared minus 1 over 3 factorial, 2 cubed, plus 1 over 4 factorial, 2 to the 4 minus da, da, da. Now, again, you could leave it here if you like, because, we didn't really find a nice formula for this one. So, the formula here, but it turns out this one has a nice formula. It's just this C naught x to the half times this, n equals 0. 2 to the n, it alternates 2 to the n factorial, like that, x to the n. So that's cool. But I like I said, I'm easy peasy. So you can either leave it like this, or you could leave it like that, as long as you went out a few terms to kind of see the pattern. And then the last little bit is that we just write the general solution. So the general solution is that, let me call that y2. Now here's what I meant by, we have to be kind of careful. This C naught here is not the same as this C naught here. So you just want to kind of give it like a dummy variable or something like that. So the general solution is going to be big Y is equal to, this is what I mean by it's kind of hard. So it's kind of C naught Y1 plus, I know I called this C naught, but this C naught is different than this C naught. They're different problems. So maybe call it like, I don't know, like a D naught or something like that, donut, plus D naught Y2. Which, you could write out pretty nicely. It'd be C naught 1 minus x plus 1/3 x squared minus 1 over 5 times 3 x cubed plus da 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 plus D naught x to the half times 1 minus 1 factorial over 2. Oh, I forgot this. X's, that was dumb. X plus 1 over 2 factorial 2 squared. Yeah, sorry about that. This should have an X. No, that shouldn't. X squared, x cubed. That's my fault. I was just jumping ahead. Plus minus 1 over 3 factorial 2 cubed, x cubed, plus yada, yada, yada. As long as you identify that this right here is like your y1, and this right here is like your y2. And that's going to be our general solution. Whew. Okay, well, that's Frobenius method Frobenius. So shout out to Frobro. He really helped us out come up with this. Otherwise, we couldn't do stuff like this. There's a couple of them that you need to do like this on the lab, the take-home exam. So make sure you look at that and have fun with it. Thank you, everyone.